screen.
Okay.
You should be able to see it, right?
Yes, we can.
Okay,
20
great.
minutes.
20 minutes, great. So,
Yeah.
hello everyone. My name is Jeffrey de Vries, and I am a recent spatial engineering graduate from the University of Twente in the Netherlands. And I will present my research about assessing the potential disruptions from earthquakes in the historical peninsula of Istanbul using 3D models. So I will present to you first a short introduction on the problem and the main objective. Then I'll dive into the methods, and then quickly on to the results, where I'll talk about the identified potential disruptions, the vulnerability, risk, and analysis of these disruptions in my case study area, and I'll show you the 3D models that I created. And then lastly, I will give a couple of recommendations for interventions, and I will tell you some of the limitations that I had. So yeah, the reason for this study is basically that the mainstream planning approaches that try to reduce earthquake risk provide actually static solutions for a very dynamic and complex environment where unexpected disruptions can occur. This dynamism is caused by the many interrelated components in a megacity, such as the people, built-up environment, and the organizations. And as you know, I'm talking about Istanbul, which is a huge city with currently over 50 million inhabitants, including 1.6 million migrants, and which is known to be increasingly prone to earthquakes. As you can see here in the picture, there's a east to west progression of epicenters along the North Anatolian Fault. And as a consequence, experts have predicted that an earthquake of at least magnitude 7 will strike Istanbul within the next 30 years. So for my area of focus, which I've shown here, it includes of 3 neighborhoods within the historical center of Istanbul called Fatih, which is very important for its culture, the history, and of course for traffic. Besides this, there is a major hospital located in my area, which of course needs to remain accessible during such an earthquake event for emergency aid. That's why this study analyzed the root causes of potential disruptions that impact the traffic control specifically, such as evacuation and emergency services, using the 3D models. In order to do so, it was divided in several tasks. The first aim was to identify actual potential disruptions that might happen in my area. And for this, I did a literature review in which I analyzed 3 historical earthquake events where the earthquakes impacted the traffic control. And I will introduce these events later on in my presentation. After this, I assessed the vulnerability and risk in my area and analyzed these identified potential disruptions. Throughout the study, I decided to distinguish between 4 different types of vulnerability and risk, which include socioeconomic, road, building, and systemic vulnerability and risk. For the road, systemic, and socioeconomic vulnerability and risk, I applied the additive normalization indicator-based approach. And for the building and vulnerability and risk assessment, I applied the EMS 98 macroseismic method. And the reason for applying a different method is that with the last one, you can get a more realistic idea on what the expected building damage is instead of just saying low or high risk. In both approaches, I basically combine a couple of indicators that represent the vulnerability, as well as the different hazards that can occur in my area, which for my case, included the earthquakes, but also the resulting fires and liquefaction. And these applied hazards were based on the worst case scenario, according to another study from JICA. After this, I created 3D models to get a better understanding on the underlying causes of these disruptions. For this, I used procedural 3D modeling, during which I basically apply so-called CGA rules to extrude 2D building footprints and create a level of detail 1 block model. I applied a realistic texture to the roads, and I applied a green to red color scheme to represent the vulnerability and risk from low to high. And then based on this, I identified the additional value of the disaster risk reduction of an additional value of 3D models in disaster risk reduction, and I made some suggestions for to make the area more earthquake resilient. So now we go on to the results. Like I said, I identified potential disruptions by analyzing 3 historical earthquake events. The first one was the Christchurch earthquake that happened in New Zealand in 2011, where especially the liquefaction caused a lot of damage to the buildings and the roads, like shown here in this picture taken in the CBD. I also analyzed the Tohoku earthquake that happened in Japan in 2011, where the earthquake and the resulting tsunami caused a lot of damage and the debris that isolated several areas, as you can see here. And I analyzed the Kobe earthquake that happened in Japan as well in 1995, where the transportation capacity of the area was reduced to only 5% as important highways were destroyed, like the one shown here. So based on these events and the local characteristic of my case study area known from literature as well as fieldwork, I decided to focus on disruptions, the damage to the road network, road blockages by debris, traffic congestions, and communication issues between emergency services. So now the vulnerability and risk assessments. Here I show the socioeconomic vulnerability and risk. And as you can see, there is high socioeconomic vulnerability in my area caused by indicators that express the low risk awareness and preparedness that is there. Besides this, in the picture on the right, you can see that it's especially very vulnerable here located in Molakarani. In the picture on the right over here, you can see that there's also medium to high socioeconomic risk. And as a consequence of this, it's likely that the people will behave very inappropriately during an earthquake, as they just do not know what to do and how to act. And that's why it's possible that there will be a lot of traffic congestions, as there will be a lot of chaotic evacuations, and that might obstruct the emergency services. But there might also be communication issues between the emergency services due to an overload of the communication networks. Here I show the road vulnerability and risk. And as you immediately see, there is low to medium vulnerability and risk, which means that the roads are not that damage prone. It's very likely that they will remain passable during earthquake event because they will not be destroyed. There's only slightly higher risk for damage for the narrow roads that are smaller than 8 meters wide here in Cheremini. In contrast, buildings are very prone to damage. This study found that around 75% of the buildings in the area have vulnerability class B or C, which are 2 of the lower, more vulnerable building classes. Which actually makes a lot of sense because the area that I have consists of a lot of low quality buildings. As a result, this study determined that almost 90% of the buildings have will receive damage grade 3 or 4 during the applied earthquake event. This means substantial to heavy or very heavy damage. The most damage prone buildings are again located here in Molakarani, which you can see from the lot of orange coloring that is shown in the map. And they mainly exist of masonry type buildings. Such buildings can, of course, cause debris when they are being damaged, and that might end up on the road. So that's why I did an additional road closure analysis. Yeah. So based on the height of the buildings and their damage grades, it was determined that almost half of the roads in my area are at high or very high risk to being closed by the debris from buildings. And these include especially the narrow roads, again, here in Molakarani and Cheremini. However, the locations of such blockages in my case study area might cause the entire area to become isolated except for the main road. Lastly, we have the systemic vulnerability and risk, which you can immediately see is low or medium. This means that the area will likely, that the emergency services will likely reach the area quite quickly. There's only lower accessibility here in the south and southwest of Cheremini around the main road in Mulegrani. So these parts will become a bit more difficult and time consuming to reach for the emergency services. So all of this was input for the visualization in 3D for the 3D models. In order to show you that, I created a video that goes through the 3D environment that I created. So what you immediately can already see is that it's just more clear how the area looks. And this helps in understanding the morphology of the area. And that is in comparison to just a 2D map. An example is here, where you can see how tall and densely constructed these buildings actually are. Here we move to building damage and road risk, and we go to an area where you can see that the road is colored green, which means low risk to damage, but there's actually systemic or medium systemic risk. So there are other aspects that will make it difficult to reach. And here we have building damage and road closure risk. Here in the middle road, which is colored red, there's a very high risk to being closed by debris. This can be explained by the tall buildings, which are relatively tall in comparison to the width of the road and are also damage prone. This road closure risk reduced when we move over here and we have lower, less damage prone buildings, but also over here where the buildings are damage prone, but their relative height in comparison to the width of the road is less. And the same goes for here alongside the main road of the case study area. Here we move to the hospital, and you can see that it will largely remain accessible during an earthquake event. And another major road is here, which has a higher road closure risk. And to show you this better, I will add debris, as you can see, and it has quite some debris as well. But also this road has even more debris and a higher road closure risk. And that can be explained because these buildings next to it are relatively taller in comparison to its width than the previous road that I showed. So this is an example showing how the height information helps in understanding the road closures that can occur in my area. Besides this, 3D models have shown to be a bit more convincing in communicating that other disruptions such as traffic jams are more realistic because it's just clearer how dense the area actually is. So to answer the question, what the additional value is of 3D models in disaster risk reduction, we can say that it helps in understanding the morphology of the area, and it contributes to the understanding of and communication of underlying causes of disruptions, which were mainly road closures in my case. And this can help decision makers in suggesting more local measures and disaster coordinating organizations to prepare more dynamic action plans. So as based on this research, I suggested 5 interventions, structural measures as well as non-structural measures. The first is to seismically retrofit weak buildings, and this can protect the people, their businesses, and prevent these road closures that I showed. The weak buildings that I suggest are appointed here in blue, and these are buildings that have been determined to be damage prone, but also have shown to contribute a lot to these road closures. So in order to make the functionality of the traffic control more resilient, these are the ones that should be strengthened. Another measure is to introduce local gathering facilities for spontaneous rescue teams. Such teams can consist of volunteers, which are known to be very important during the first stages after an earthquake. Here in blue, in the picture on the right, I've shown the locations for these facilities, and these are places which have been determined to remain accessible during earthquake event, and therefore are great starting points for rescue activities or cleanup activities, or for the storage of useful resources, such as tools to remove debris or medical aid kits, for example. And in purple, I've shown additional locations for fire hydrants. These places were determined to become isolated during an earthquake event. So by placing additional fire hydrants there, we can help the firefighters in fighting these fires that become difficult to reach for them with the large trucks. Besides this, it is of course important to raise additional awareness, because to prevent this inappropriate behavior that I mentioned before. We could offer incentives for the people who do not have a lot of money due to their socioeconomic circumstances or having other priorities like illnesses. So by offering this, they could still take risk reduction measures themselves, and we could promote the micromobility based on another research that analyzed the micromobility in different cities around the world. It was shown that it reduces the amount of cars and taxi rides in the city and creates more open space. So for my case study area, this could help in reducing the chance for traffic congestions during an earthquake event that would obstruct the emergency services in their activities. So a couple of limitations. First of all, by having done additional literature review, I found that my study looked at the most common disruptions from earthquakes, but there are also, of course, others that could occur in my case study area, with like the loss of power systems or untrained personnel. So if I would have included these, that could give me additional directions during my analysis and things like that and my research. For the vulnerability and risk assessment, I had to exclude some indicators or use proxies due to a lack of data, and this could, of course, have affected my results as well as the interventions that I introduced. So that having more data would be a suggestion for future research. And lastly, it was suggested in another study to use level of detail 2 for a 3D model that is of the size that I had. However, due to time limitations, I was only able to do a level of detail 1 block model. And just having a higher level of detail could make the model more realistic, and therefore maybe the communication more easy for this morphology of the area, etc. However, we should not go into too much detail, because that would just divert the attention from the cause actually of the models. So a short recap: this study analyzed the potential disruptions that could occur as a result from earthquakes in the case study area using a multi-hazard risk assessment. And this showed that there is very low risk awareness and preparedness in the area that could result in inappropriate behavior during an earthquake. And there's high risk for building damage, which could lead to half of the roads having a high risk for being closed by that debris. And in addition, I introduced the 3D models for the visualization of disaster risk. And by visual interpretation, it was determined that 3D models increases the understanding on the morphology of the area and support the communication of these underlying causes of the disruptions. These were just the references that I used in my presentation, and that was it. Thank you.